So one more thing I'd like to cover with polygons is how to find the area of them. This comes up actually more often than you might think. Knowing the area of a polygon is used, for example, in physics simulation or in other contexts. And it's a really cool and simple formula for how to do it. So I like to show this. Oops. Okay, so finding the area of a polygon. So we're going to use what's called the Surveyors Formula. This is quite famous. It's also called the shoelace formula. You can look up why. It comes down to how the math is done. So first, let's remember something from the math unit. If I have a triangle and I have two edge vectors, then if I take the size of edge 1 cross product edge 2, the magnitude of that other vector, that represents the area of the quadrilateral made by those vectors. And I divide that by 2, I get the area of the triangle. Now what's really important for this one, for this formula, is that it's assigned area. As we learned, if we go counterclockwise in a right-handed system, it's positive. If we go clockwise, it's negative. Cool. So using that information now, I can show you how to get the size of any simple polygon. It's really cool. So this example, oops, let's try this a little differently. This example is actually, we'll use a convex polygon, but this exact thing works for concave. And if you don't believe me, you can sit down and do a couple by hand. I actually tried to get this to make my example using a convex polygon, but it was just too messy, and so you couldn't really see what was going on. V3, V4. Now notice this is a clockwise winding. It doesn't really matter. Okay. So what we do is first we draw a vector from the origin to the first point, like that. And then what we do is we take the cross product of that vector to the first point. We take the cross product of that vector to the first point and that first edge vector, E1. And so I'm actually just going to draw in this line here. So if I take the cross product of this first vector to V1 and the edge vector 1 here, I'm going to get this whole region here. It'll give me this area. Cool, right? And divide by 2, of course. So I'll get this. Neat. So then I'll do the same thing. I add in the cross product of the next vector from the origin to V2 and edge vector 2, the next edge vector, so V2 to V3. And so if I draw in, it'll give me this triangle. So again, cross producting this one with edge vector 2, like that. And I get this triangle here, and it'll give me the area of that, no problem. So I add them together. You can already see that we're getting too much area, right? We're getting this region at the bottom here, which doesn't belong in our quadrilateral. But let's just keep going. Now, I draw from the origin to V3, and I take the edge vector 3. I cross product those to get the area, and I'll get this region right there. Okay, and I color that in. So far so good. Now what's interesting is, as I go all the way around, if I now take this last one, V4, and I take the cross product with the other one, now it's the opposite winding. Every other one has been clockwise winding, clockwise winding, clockwise winding. This last one is going to be counterclockwise winding. So this edge vector, where's my green? This is edge vector 4. I'm going to cross product this with this last blue line right there. So I'm getting the opposite winding, and it's making this triangle down here. So this is the triangle it makes. But because it's the opposite winding, that cancels out. It subtracts it instead. So then what I'm left with is this yellow area, which is really cool. So it doesn't matter whether it's clockwise or counterclockwise, because it's the opposite that matters, the fact that they cancel each other out. So any opposite winding will cancel out. And this also means it works for concave. Like I said, I tried to get an example for you, but they get so messy. But basically, if I'm doing something similar, where's my green? If I do something similar, when I go concave and I come back out, you add these ones, these triangles that it'll make. In this backwards section, you actually will subtract the region with the subtraction. So if you try it out, you'll realize that it'll subtract that and you won't overcount. It's really clever. It's really cool. If you're more curious, I recommend checking it out online. So you add all those results together and you get the area of the polygon. Now this works for any simple polygon. So no complex ones, no holes, no overlaps, that kind of thing. And if I give you a generalized formula, we get the signed area. Now it's signed because winding still matters, right? If everything's clockwise and then I go the other way, I'm going to get a negative result. If everything's counterclockwise and I cancel out positive, I'm going to get a positive result. Cancel out negative. So the winding matters. So the signed area still tells us something. Signed area of a simple polygon. And this is the actual formula in general. And you can do, if you do the cross products yourself, you can see how it cancels out. It becomes very clean and very easy to calculate. So I'm going to sum I equals 1 to n of x at I times y at I plus 1 minus x of I plus 1 y of I. Now again, how all those cross products collapses into this, I'm not going to show, but this is really nice. And the only other notes I'll make here is that because of this plus 1, n plus 1 is going to be the vector 1. You know, basically it's a modulo. It loops around, okay? And the other thing is, yeah, I give x's and y's, you know, for vertex n, that's going to be x of n, y of n. I suppose I should say vertex of I. So vertex of I equals x of I, comma, yi. So the Surveyor's formula, it looks really complicated to get an area of a polygon, but you can see with just 2 multiplications per vertice and a subtraction, we can calculate the area. This is really powerful. The only other notes I want to give is that the sign does give the winding. Okay, sign gives a winding, which is nice. As I said that before. And like I said, this has many uses, including physics simulations, and it'll come up from time to time. Such a cool, simple way to calculate that. Okay, that's a short one, but this is all we're going to say about polygons. We're done with polygons. Thanks.